Okay, are we live?
Yep.
All right, guys, well, thank you so much for coming. Let's get started here. Applications of quantum computing. Let's dive right into it. So on the agenda today, first of all, you can see that they've updated the AI capabilities inside of Google Slides. So now all of my slides look incredible, which is a huge upgrade for me. So we're gonna start with a review. So as you guys are aware, this is the third workshop that I've hosted. So previously we did hardware, algorithms, and software, and today is the fourth and final one on quantum applications. We're going to focus on four main applications, which I believe are the most important. We're going to focus on optimization problems. We're going to focus on chemistry, AI, and cybersecurity. And then I'm also going to talk a little bit about business in quantum and how to be successful in quantum computing going into the future. Okay, so a little bit of a hardware recap. So this is the third time we've talked about quantum hardware because I've introduced all the other lecturers talking about it as well. We'll just kind of focus on some of the images over here. So anyone know what this is here? Anyone recognize what that might be? So that is a quantum fridge. So it's basically something that keeps the components extremely cold because a lot of them need to be close to absolute zero, minus 273 degrees Celsius. So that is a piece of technology that allows that to be possible. And then here is just showing some different types of quantum hardware. So this up here is Microsoft's Majorana 1 chips. This is a completely new style of quantum technology that we kind of discussed it in our hardware lecture, but it uses topological conductors, which is a new state of matter that Microsoft created in order to make this chip. Here we have a laser-based quantum computer. These are superconductor-based quantum computers. So just trying to show off here that there's a lot of different types of quantum computers, and they're quite different in their operating physics. And then just a little bit of other information. So there's two types of qubits. There's physical and logical qubits. So a physical qubit would be for example, one of these are called Josephson junctions. Each one of those could be, in theory, a physical qubit. But in order to reduce the error in a system, sometimes you need up to 1,000 physical qubits to make one logical qubit. And then that logical qubit is what you can actually code with using quantum software. So right now, IBM has arguably 1,000 physical qubits, which, as I discussed, that 1,000 physical qubits may only be one or two true proper logical qubits. So the reality is we need millions, if not a billion plus physical qubits in order to have useful quantum computation. There's type uncertainty. So as I mentioned, there's a lot of different types of quantum computers. It's not clear which one is going to become the dominant style. So there's a lot of uncertainty with that. And then decoherence at scale. With modern technology, as we add more qubits, it's called decoherence, but basically means the noise in the system grows. And it makes it so these computers become useless as we scale qubits right now. So a lot more science and engineering needs to go into this field. Okay, quantum computing approaches. So there's three different types of general approaches. The first off is gate-based. This is how most quantum computers work. You create these things called quantum circuits, and then there's a class at this university where students are forced to learn about this kind of stuff. Another style is quantum annealing. This is where you kind of set up an quantum wave landscape, and then you reduce the energy in that system and allow it to converge on an answer. That's just another style. And then there's continuous variable, which I wasn't actually very knowledgeable about until I started doing research for the previous presentation I did, but these use something called Q modes and are quite different. So again, highlighting that there's very different approaches as well in terms of the actual logic behind the computers. Okay, moving on to review quantum algorithms. So quickly, what is a qubit? So in normal computers, we of course have 0 and 1s, whereas in quantum computer, we're kind of somewhere in between, and we create a probability of being either a 1 or a 0, and it kind of gives us this randomized probabilistic approach. I kind of mentioned up there, but something we discussed in our quantum algorithms workshop is the fact that when we structure our qubits like this, they kind of, as you can see here, it's kind of on a circle. And when we have circles, we can connect that to imaginary numbers because of Euler's formula, which is something that you may learn if you take more advanced math courses. And then because we have access to imaginary numbers, we just have a larger amount of mathematical operations. So in a simplified sense, that's why quantum computers allow us to do algorithms that you can't do in classical computers, because it unlocks imaginary numbers. Okay, quantum information. So by unlocking those imaginary numbers, we have access to three very powerful properties. The first one is superposition. So these are kind of AI-generated images of a theoretical atom, and then these are the electrons around that atom. And you can see that the electrons, it's in a space. It's not at a particular point. It's in a superposition. It's like a cloud. So it exists somewhere within that superposition. That's one of the main properties. Another property is interference. So since quantum exists in these kind of clouds and waves, if we overlap them, We can have constructive or destructive interference, which is a powerful property. And then finally is entanglement. So we can merge different qubits into one state, and that allows us to kind of have a very rich representation of multi-state systems. So this is a little example. This is the punchline of a longer example that was in the quantum algorithms workshop. The idea here is that we have a 2-qubit system, and we've entangled them. So that's why in this bracket, there's 2 qubits here. But in a 2-qubit system, if we put them in a superposition, we can actually turn those 2 qubits into 4 states, as we've done here, 0, 0, 0, 1, 1, 0, 1, 1. And using those 4 states, which we built using entanglement and superposition, we can create a series of waves. And this is kind of a little bit AI generated here, so don't look too closely into these waves. But you can imagine that each of these 4 states represents one of these waves. And then by interfering the waves, we can arrive on converging on the solution to the problem. So that's how a lot of quantum algorithms work, is we use superposition and entanglement to build a series of states. Each of those states is represented as waves. We then use interference property to merge those waves, and then we converge on an answer, high probability of measuring the proper answer. Okay, fantastic. Moving on to quantum software. So as we discussed last time, there's a lot of different software languages. Up top there are kind of the big ones, Qiskit, IBM, and there's quite a few. One thing that's interesting to note is the languages vary in hardware level abstraction. So what that means is some languages, like Google's CERT, is very low level to the hardware, so you're interacting very much at like the physics level almost with the computer, whereas Qiskit is built right on top of Python, so it's very high level and can easily be used with other non-quantum programming. It's important to know as well that most languages are specific to a particular computer, so as we already discussed, all the hardware is very different and it's based on different physics, so naturally you need different compilers and you need different programming languages in general. What's interesting is Amazon Braket, they're actually working on a quantum language that can interface with all the computers, so that's going to kind of become an interesting standard if they pull that off. Something we discuss in detail as well is the question of the quantum advantage. So we know that in certain situations quantum computers are useful, but the reality is that for a lot of things, classical computers might be just as good. And we kind of see that a lot at like the project level, where people will work on projects that in theory would actually can technically use quantum computing, but it might actually be slower or more resource intensive than just using classical computing. And as well, this like little note here at the bottom. So right now, the way that it works when you run these quantum computers is sometimes you can use a simulator. So you're really running on a classical computer, but it's like simulating quantum. Or you can actually pay to use some qubits. Like IBM, I mentioned they have 1,000 physical qubits. They've merged those into, you can choose between like 1 or like 72, I believe, logical qubits. So you can pay to use like up to 72 logical qubits. But as you guys know, like having coded things yourself, 72 bits or qubits doesn't really get you that far. So even if they stretch it out to 72 qubits, it's like still arguable how useful that is at this time. And then the other thing to note as well is in real life, all of the useful quantum systems are quantum classical, meaning that we still use classical computers for data storage and data transmission, and kind of some parts of the algorithms that you could look at would also contain classical components. So just being aware that you're never only going to be using a quantum computer, you're also going to have a classical computer involved as well. So I'm trying to get in here. Hey, yeah, of course. All right, moving on here. So this is now stepping into the applications. So optimization, this is one of the big four applications of quantum computing. And this is the one where I think there's the most financial value in my opinion. So there's a few reasons why quantum computers are very advanced for optimization problems. So the first thing to discuss is cursive high dimensionality. So imagine you're trying to optimize a system and like, let's say it's like, I'll discuss this example later, but delivering packages for Amazon. Every day they deliver 20 million packages, people are canceling, people are adding new orders, like the dimensionality of this problem is extraordinarily high, and it's bounding on impossible to properly do using a classical computer, which is right now they use called heuristics, which is basically they make a best guess, but it's mathematically not perfect. So there's kind of the curse of high dimensionality where they can't actually model these enormous problems with classical computers. Kind of a related topic is parallelism. So a classical computer needs to kind of measure and test each possible path at once, whereas a quantum computer can kind of test all routes at the same time, relating back to that logistics Amazon problem. And the other thing too is avoiding local minimums. So classical computers often get stuck at local minimums as they're trying to optimize a problem. but there's quantum computing tools which actually absolutely allow you to reach those global minimums. So those are the main reasons why quantum computing is so powerful for optimization. And yeah, let's talk about some use cases. So this is what's quite interesting, and some of these are quite recent. So this one is really cool. So logistics. So Beijing Airport has apparently 10,000 taxis that they operate with. And you can imagine that if all these taxi drivers put into Google Maps, like fastest route to the airport, it would all take them on the same path, and they would actually be creating their own traffic of just taxi drivers because they have so many. So using a quantum computer, they're working on a pilot where they can kind of optimize a route where like 100 drivers go this way, 100 will go this way, and you can imagine that this problem becomes very high dimensionality, which kind of naturally leads to being a quantum problem. So it's quite interesting. As well, finance is a big one. Our club has some projects in the quantum finance space. Similar to the logistics problem, when you're trying to model finance, especially if you have a lot of different companies that you're trying to model a lot of different possible situations, the dimensionality can become extraordinarily high. So yeah, JP Morgan Chase is working on portfolio and risk optimization, and apparently they've been investing billions of dollars into this. I don't know if that's in actual hardware or if that's in kind of growing the talent, but yeah, there's definitely some obvious use cases in finance and risk and return modeling. And then this one is really interesting, this engineering use case. So Boeing is working on a pilot right now where inside of the airplane wings, there's a lot of fibers, and these fibers can be oriented in any direction, and they can have an origin starting anywhere. So it's a very high dimensionality problem, like how you want to optimize the position of these fibers. And obviously you want it to be as strong as possible and as light as possible. So they're using a quantum computer to try to model the optimal amount of strands and their optimal diameter, optimal position, in order to kind of be as light and as strong as possible. So that's a really interesting use of quantum computing as well. So future use cases. So kind of building on what's already been done in finance. As I kind of mentioned, there's going to be there's a lot of risk modeling that is possible when you kind of are able to access those high dimensionality algorithms. Amazon, I talked about it, 20 million packages a day. They do everything from manufacturing to international logistics to at-home delivery. So the amount of dimensionality that they're dealing with is extraordinary. Absolutely could benefit probably millions of dollars per day if they had optimal quantum solution. And then engineering, so another one is power grid. So there's power generation all over the power grid. Power needs to be moved. We need to be able to predict how much power the demand is going to be at certain times. Super high dimensionality problem. And last year our club actually did a project trying to relate to this. But yeah, that's just another huge application that governments could use related to quantum computing. So tools for quantum optimization, this is kind of leading back into the algorithms. So these are just a few different algorithms. So quantum approximate optimization algorithm. So this is a hybrid, this is a quantum classical, I believe, hybrid algorithm. I'm just kind of throwing these out there. So these are something that you could look into in the future, but these are the type of algorithms that you'd be using for optimization problem. There's also Grover's algorithm, which is very famous, and it's kind of a search algorithm. And then quadratic unconstrained binary optimization. This is like a type of data structure that quantum annealing computers can accept, and those can be used for optimization. So those are some of the big tools. Moving on to the next use case, so chemistry. So real chemistry is based on quantum phenomena, and at first, I didn't realize this initially, but when I was thinking about this, when we talk about chemistry, we talk about atoms, and they're quantized naturally, because the word quantized and quantum means the smallest possible piece of something. And when you think about it, an atom, all these elements, those are quantized matter. So really, chemistry is absolutely just quantum at the quantum level. Which makes it very natural for a quantum computer to model, because when we try to model it with classical computers, we reach certain limitations. I kind of say there's two different flavors, two advantages to quantum computing and chemistry. There's direct quantum level modeling, which is kind of what I already described. And then as well, we can use the optimization techniques that we discussed previously. Some of those can apply to chemistry as well. Definitely huge use cases here. Drug discovery, advanced science research, material science, molecular engineering. Right now, some people would doubt that there's a lot of optimization use cases. I kind of think it's over time we're seeing that there are a lot, but some people would doubt it, but pretty much no one doubts that there are advantages to chemistry using quantum computing. This is a very clear use case. All right, cybersecurity. So this is probably something that people hear a lot, is that when quantum computers get good enough, using Shor's algorithm, they're able to crack into a lot of the cryptography that we use today. I kind of find this, it's definitely an interesting thing, but I believe that there's a lot of work right now going into quantum safe cryptography, and I believe that by the time some malicious hacker has access to a quantum computer, our information will be brought into a quantum safe environment, at least most of it. So I'm not too concerned about this, but it is absolutely a use case. It's not even in cybersecurity, it's more of a use case in cyber attack using Shor's algorithm, but it's something that often comes up when we talk about applications of quantum computing. One thing that's interesting to know is there are some cybersecurity use cases where we are using quantum computing to kind of secure data. And there also are post-quantum cryptography, which I discussed a little bit, which is quantum safe, but a lot of these are not using quantum computing. They're using classical computing to make things not vulnerable to quantum computing. And I believe we have a project going on right now that's relating to this, because there's, I don't know exactly, but there's certain ways to encode information geometrically, which a quantum computer doesn't have a natural advantage over. Yeah. So last thing I want to talk about here is quantum AI. This is a little bit of a larger topic. I was possibly even going to run a whole workshop on this, but so one thing that's interesting is called like a quantum feature map. So if you guys are aware, like when you have a neural network in AI, you need to run it through a nonlinear function in order to kind of allow nonlinearities to be captured. And quantum can act as a very powerful kind of nonlinear mapping. So that's kind of a huge use case there. Another interesting one is quantum neural networks. So in AI, we use neural networks. Different parts of neural network can be used for different things. We can have one layer of it that uses qubits and kind of brings that classical information into a quantum state. And then when we're in that quantum state, you know, we can run quantum algorithms or like even allow those math to interact at like in the Hilbert space, which is the mathematical space where quantum computing exists. So there could be some interesting advantages there. This has not really been done that much. So it's unclear whether this is just kind of interesting or there's huge benefits, but it's possible that there could be some interesting insights if we use quantum neural networks. The last one here is, or third one here is quantum gradient descent. So as you guys are aware, in AI, we have a loss function, and then we always try to reduce our loss function. We like descend the gradient, and sometimes we can get trapped in local minimums. Sometimes it can be quite inefficient, but as we discussed earlier, optimization is one of the main use cases of quantum. So we can apply those quantum optimization techniques to try to optimize our loss function and do gradient descent. And then lastly here is quantum enhanced data sampling. Classical computers can sometimes struggle to sample data from a high dimensionality space, whereas quantum computers can very naturally do that. So yeah, these are 4 big use cases here for quantum and AI. So moving on a little bit to quantum business, I would call it. I was thinking about this. So that I'm kind of proposing a theory called the $1 million prompt theory. And the idea here is it possible to make a lot of money for doing a relatively easy quantum implementation for a business? So what this means is there's a business problem, some business has an issue, and someone like us in the year 2040, 2035, right as quantum is becoming good enough to be useful, but before it becomes super mainstream, there'll be opportunities for a quantum formulator like us to come in and structure their business problem in a quantum acceptable form. And then now that it's in a quantum acceptable form, you can then move that, like, you know, do an AI prompt, like this is my problem, here's my data structure that's quantum acceptable, and then you could come up with $1 million business solution very simply. So that's kind of what the $1 million prompt theory is. Hopefully one day I'll be able to enter some company and very quickly be able to formulate a quantum acceptable form of their business problem, and then that could become a very valuable solution. So it's only a theory at this time. It's yet to be seen whether or not this will be possible, because it might be the case that only enormous businesses have quantum use cases, and those businesses would be working directly with larger quantum computing companies. But if there's a lot of use cases for small to medium-sized businesses, there will absolutely be a lot of people who are making a lot of money and providing a lot of value very quickly. $1 million prompt theory. So that kind of leads me into this next topic. So how to be successful in quantum technology? I kind of see 2 different paths. We'll kind of start off with path A, and it's more traditional, I suppose. So I graduate with a STEM undergrad, pursue higher education in quantum, become an expert in something. So this could be highly specialized, especially as you pursue a research-based PhD or master's in quantum computing. You'd be doing something exceptionally specific. And unfortunately, a lot of people, like let's say you do your PhD in something very specific with the laser in this one particular quantum computer. Unfortunately, especially if a different type of quantum computer becomes viable instead of laser-based quantum computers, that skill may actually unfortunately become useless. But yeah, become an expert in something and then kind of try to tailor that to something that's, I guess, likely to be industry useful. Especially if you're focusing on algorithms, that's probably always going to be useful because all the computers in general can use the same algorithms. But if you're hyper focused on the hardware, there could be some risks there. Anyway, and then eventually get well positioned to get a job in quantum computing. And then yeah, I'll talk about it in like a future slide, but I think kind of a decade or so is what we're looking at before there's serious momentum in quantum. So yeah, just kind of theoretically, that's a path A to become successful in quantum. Path B would be to start a career unrelated to quantum, monitor quantum developments closely, focus on quantum integration skills. So that's what I kind of talked about in the previous slide, where you go into a business and then you implement quantum knowledge into that business. So focusing on implementation and integration skills. And then finally, you can start a business or join a quantum integration business. That's kind of the path B there. So this is kind of involves kind of waiting for the right moment and then hopping on the integration implementation. Because unless you go do your PhD, you're not going to be able to build your own quantum computer. You're not going to be able to capitalize in that way. So you're best off kind of trying to focus on the integration implementation. So yeah, those are kind of the two different paths I see in successful in quantum technology over the next decade or so. Just for fun, I'll kind of share my plan with you guys. Kind of a mix of A and B. So I'm completing my engineering degree in biology or undergrad in engineering and biology. I'm planning to start a career in engineering industries, not necessarily relating to quantum computing. I'm going to keep very up to date on quantum technology. You guys know I do that by delivering these presentations. I'm going to let my network know I'm interested. So all of you guys in the future, you start a business, let me know. I'm informing my network that I'm interested in this. And then I'm going to study quantum computing at the University of Calgary once the technology matures. So they have quite an interesting one-year program there, and it's actually meant to be done while you're working. It's like a professional degree, and it's not focused on advanced science. It's actually focused on business applications. So it's pretty enticing to me, especially if we see some good momentum in quantum technology. That's something I could pursue in the next decade, kind of part-time, and slowly get that done. And then maybe one day I'd like to attempt to prove the $1 million prompt theory. I'd like to turn that theory into a law if possible. All right, fantastic. We're wrapping up the presentation here. Just a few other things to keep in mind. So high valuations in quantum. So let's talk about a company called Xanadu. I actually visited their head office in Toronto about 1 year ago. Cool company. They're working on some laser-based quantum computers. And they have awesome lasers, they have smart people, but they don't really have any real revenue. So their business is kind of very much research and development. So their revenue is likely under 10 million. But look at this. This year, they had their initial public offering at $3.6 billion. So this isn't matching this revenue, especially when their profit is certainly, I wrote, exceptionally far from profitable. I don't want to be offending any Xanadu employees if they're watching this video in the future, but the finance here doesn't make any sense. The company should not be valued at $3.6 billion. So kind of the idea here is people are making money even if the computers don't work, right? The executives at Xanadu, they just got $3.5 billion. They don't have a working computer. They don't really have any clients, but they have billions of dollars. So the idea here is people are making money even if the computers don't work. I was speaking to someone last night, and they were kind of informing me about kind of quantum technology, and like they're coming from a more investor perspective, and there definitely is a lot of hype that isn't always relating to reality. So yeah, just a bit of comments on my timeline about timeline opinion. So I believe that we need a lot more qubits to have useful computation. I think we need about 1 million times more qubits. So even if we 10x qubits every year, which is aggressive, it still takes us 6 years to get about 1 million times more qubits. So yeah, that's something to keep in mind is we're very far from having enough qubits to do useful things. I believe 10 years is a possible timeline. 10 years from now, we could start seeing Beijing might finish their taxi implementation. I believe 10 years is a reasonable timeline, but again, people have probably been saying that for decades. And then lastly, I believe that robotic is here, not quantum. So this is kind of a bit tangential, but I think that we're entering a phase of extreme robotics. Like a robotics era is like coming this year, next year, but I think quantum is still down the road. I was kind of discussing with that same person I was talking to last night, and not that we were in an argument or anything, but he was kind of saying, I think quantum is coming before robotics, but I'm very confident that it's the other way around. That's a bit of my opinion there. And then yeah, it's kind of ending up here. So problems in quantum applications. So there's the same problems with hardware limitations, which we discussed, algorithm limitations. So there's only a few useful algorithms. As we kind of discussed in this presentation, even though there's only a few useful algorithms, you're still able to do quite a lot of useful things with them, but it's important to note that there are algorithm limitations. And what's been interesting as well is because of AI, there's been some previously believed applications of quantum computers and some algorithms that initially we believed would be better than classical, but AI has proven that using AI, it's actually worse than classical computing. And then this is a big question here. So Will quantum computers only be useful for huge operations? Will medium-sized businesses be willing to pay for quantum? So that's something that we don't know. So hopefully medium-sized businesses will be willing to pay for quantum, and that would allow a lot more opportunity for entrepreneurship and business in quantum. Whereas if it's only huge companies like Amazon, they're going to develop out their own quantum team, and it will kind of become a very niche part of the market only for enormous businesses. As I kind of mentioned, there is extreme hype in financial markets. Investors are not very knowledgeable, and companies are grossly overvalued. And then something else as well, I was doing some research on this, and many figures combine quantum and AI to inflate the apparent value of quantum. So to talk specifically, so I was looking at this one statistic by McKinsey. I don't have it on here, I forgot the exact number, but they were estimating, they said quantum and AI will save whatever billions of dollars in this particular industry. But they purposely, in my opinion, are mixing quantum and AI, because 99% of that savings is probably from AI, but they want to like overhype quantum for whatever other reasons. So they're including the words quantum in that statistic, and it's, in my opinion, almost purposefully inflating the apparent value of quantum. So yeah, I believe that we're kind of approaching the end here. So that's the end of my presentation. I tried to keep it short for you guys. Any questions or comments? No? Well, thank you guys so much for coming, and I hope you enjoyed the presentation. Thank you so much.